Welcome back, and we're going to kind of take the idea of the mean value theorem a step further. And so this is going to be a longer video. If you need to pause it and resume it at another time, please feel free. Okay, but to begin, we're going to look at this function. Okay, what does the graph look like? So it's h of x squared is equal to 1 minus x squared. Well, if you do a little manipulation and write y instead of h of x, this is really just x squared plus y squared is equal to 1. And that is the unit circle. Okay, so I'm going to do my best to draw a circle by hand. Okay, sure, that's a circle. And so we go out a radius of 1 in both directions, or in all directions. Okay, and so the question is, can we use the MVT here, the mean value theorem? Well, is this a differentiable function? Well, the thing is that it's not a function. It's differentiable, like we can do implicit differentiation, but it's not a function, right? So MVT cannot apply as it is not a function. Okay, but then let's if we go a step further and just say, okay, well, what about the conclusion of the MVT? Does it make sense here? So the idea is if we are on this interval of -1 to 1, right? Here in green would be the secant line. And then which we could, calculate the average rate of change, and the secant line slope is 0. Is there another place, or are there places on this graph where we would see the instantaneous rate of change being 0 as well, or the slope at that point? Yeah, actually, like right at the top here. So we would say like the mean value theorem seems to apply because at this point of 0 in here, right? At 0, it has a slope of 0, which is the same as the secant line slope between the two endpoints of 1 and -1. So it makes sense, but what do we do? So then what we're going to do is we're going to think a little differently. Okay, we are going to say, okay, well, maybe I can parameterize things and maybe that'll be useful too. So when we introduce parameters, I think we've seen this before. The idea is we're just going to represent each of the coordinates in terms of another variable. So in this sense, we're going to represent it using theta, where theta is the angle, the counterclockwise angle, I should say, from the positive x-axis, okay, and the terminal side, okay? So this, if you've seen polar equations before, you might remember that x is r cosine theta and sine is r sine theta, and the r is just 1 here when we're working with the unit circle. Okay, so I digress. Anyway, this leads us to saying that xy, we can really represent it in terms of just theta as cosine theta sine theta for the coordinate, for any coordinate on the unit circle. That's kind of fun. Okay, but when we do this, we're actually saying that x and y are both functions of theta, so really it should be something like x of theta is equal to cosine of theta. Okay, and y of theta is equal to sine of theta. Okay, but anyway, that's just a little bit of notation. But when we do this, now we're thinking, okay, when we do this, when we represent x and y like this, are these continuous and are they differentiable? Well, sine and cosine, last I checked, they're continuous, right? And yes, they are differentiable. So yes, they are continuous. I'm abbreviating, and oops, and differentiable, okay, on R. Okay, and the only thing we need to do is when we introduce a parameter, we need to introduce the domain or the restriction on it. And so I'm just going to say theta is going to be within the interval 0 to 2 pi, and that would give me the full rotation around the circle. Okay, so then now we're thinking, can we use the MVT in this case? Because now we have a function, we have its differentiable on a certain interval, right? We have bounds for that. Yeah, it should be able to work. And so if we continue and we have these a and b bounds, I'm just using that instead of 0 and 2 pi, we can set up the MVT as such. So this would be our equation if we were to use like the x of theta, and then this next one would be y of theta. Okay, and I used d in the case of y just so we didn't confuse c and d. It really doesn't matter what you use. Okay, but what do these mean? So if we kind of dissect this a little bit, we have to think about the mean value theorem, right? The mean value theorem still says that if that the average rate of change is equal to the instantaneous rate of change for some point in the interval. And that's very much the same thing. So I'm not going to write this down, but each one of these could be interpreted as the change in either x or y at a certain value in the interval is the same as the change in either x or y over the entire interval. Okay, the instantaneous rate of change at a certain point is the same as the average rate of change over the entire interval. Okay, but the only thing is that normally, like we want to discuss, at a certain x value, this is how it's changing. Now we have two equations to describe either x or y. We don't have anything in both. So just what we could think about is we know that y is cosine, or from our work above, is cosine of, and I'm just going to use c because again they could both be c if I wanted to do that, which is equal to sine, and then in my case the interval that we chose for theta is sine of 2 pi minus sine of 0 over 2 pi minus 0. Okay, and similarly, x is negative sine, of c, which is equal to, so this is the instantaneous rate of change, and that's equal to cosine of 2 pi minus cosine of 0 over 2 pi minus 0. Okay, and well, if I'm interested in how y changes with respect to x, let's just insert a division. Divide both sides by, or divide, I know these things are equal, so let's divide them. Okay, I can divide the equation on both sides by an equal amount. So there we have equal amounts. Okay, and so we can simplify this to cosine of c over minus sine of c, and then this is going to be, the 2 pi minus zeros would cancel out. I have sine of 2 pi. I'm not evaluating these on purpose, and you'll see why. I want to leave these as just sine of 2 pi minus sine of 0 over cosine of 2 pi minus cosine of 0. Okay? And then the only thing here is that when we do this, right, we're being a little careless. Okay, this equation is false in certain contexts. Specifically, whatever c is, it can't be 0, right? We can't divide by 0, so I know that sine of c cannot be 0, and so that means that, c cannot equal any multiple of pi. Okay, and I know c can't be anything in the endpoint, but it could potentially be pi itself. So how do I fix this? What I'm going to do is restrict my domain. Okay, and I'm going to restrict the domain to be from 0 to 2 pi. Instead, I'm going to have from 0 to pi, okay? And now, again, c has to be within this interval, and so then I won't get any places where I would be dividing by 0 potentially. Okay, so what we've arrived at so far is that cosine of c over minus sine of c, da 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 da, right? And I'm just adapting this per the mean value theorem's definition, okay? Or per our previous study, okay? And then certainly if we simplify this, we can maybe find a value of c. So the numerator on the right side is just 0, right? Sine of 0 is 0, and sine of pi is 0. So then we just get cosine of c over negative sine c is equal to 0. So then cosine of c is equal to 0, and therefore I can find that c is pi over 2. Okay, and so then does this seem to match what we thought before? And the answer is, well, yeah, it should. We had the unit circle, right? And we said the average rate of change between 0 and pi in this case is this green line. And then the red line was the place where we said, yeah, it seemed like we could find a place where the the slope is also 0. So here we said the slope is 0 between the endpoints, and we found another point specifically when c is pi over 2 where this matched. So yay! Now we did all this. What does this mean? And for that, I'm going to go on to the next video and introduce an extended mean value theorem to us.